Hello, everyone. My name is Zhuang, and I'm a final year PhD candidate at Caltech working with Evan Kirby and Keck Science. And today we're going to talk about really a big component about on my thesis research, which is a small observing program on KCWI I designed to characterize the chemical abundance of both stellar population and interstellar medium in nearby galaxies. And before I start my talk, I really want to use this chance to say thank you to everyone who have been actively working on the development and the maintenance of this amazing instrument. Without these joint efforts, this thesis won't even exist. So let's get started. So to understand the chemical evolution of these low mass galaxies, I've been collecting the data cube for nearby galaxies between 10 to the 8 to 10 to the 10 solar masses on KCWI. And so far, we have already observed 56 galaxies in total, as you can see in the plot here. So all the colorful data points on these plots are the galaxies we have observed, and I plot them on the star formation rate versus the mass plane. And just as a reference, all the gray data points in the backgrounds are the galaxies from Zhuang and the similar redshift. So you can really see that most of the galaxies in our sample fall on this star forming main sequence. And this is really because another reason why we care about this project is we actually want to build the connections between the metals in the stars to the metals in the ISM. So we thought, we probably should observe galaxies with gas in it, and that's why we need to focus on the star-forming galaxies. And another thing is really about the mass range. The reason why we pick this particular mass range is because in our previous work, we find that there might be a break in the stellar mass-stellar metallicity relation, or MZR, at around 10 to the 9 solar masses. But all the existing large spectroscopy surveys doesn't really cover a lot of these faint dwarf galaxies because they are faint. And we thought, maybe we should observe them on Keck and trying to characterize their chemical composition into great details. And that's really how this project started. And just to recap, since I'm going to talk about the chemistry for the galaxy for this talk, I will use metallicity to basically describe the chemical abundance. But the metallicity I'm talking about is not the total metallicity. But as observer, we always use gas phase metallicity as oxygen and stellar phase metallicity as iron abundance. But since we do care about the metal comparison between different phases, it's a little bit dangerous to compare these two elements directly because they form at very different time scale. This is really like comparing a fresh apple with an old banana and really trying to figure out what happened in this apple. So that's why we need to actually search for the old apple. And here comes the magnesium. Magnesium is another alpha element, similar to oxygen. They were both created by the Quirk-Lapse supernovae. So in principle, we kind of expect magnesium to track oxygen a little bit closer. Yeah, so that's pretty much like the three elements I'm going to talk about today. To determine the oxygen abundance is quite straightforward. We just make use of the empirical calibration, the strong line calibration based on developed by Piliogin et al., which is based on the local H2 region. But it turns out that the stellar abundances measurements are much more complicated. With other existing stellar population synthesis code, we will not be able to directly determine the stellar abundance of iron and magnesium in these star-forming galaxies. And to basically, we have to come up with a new approach, which we call the two-step method. And for the time limit, I'm not going to talk too much details in it, but if you're curious, feel free to check the paper, especially if you want to make the similar measurements. And for this talk, I'm also going to focus on the measurements based on the integrated spectrum because we want to maximize the data quality. So you can really see an example of how nice the spectrum is like. I plotted them actually on log scale so that I can see all the stellar absorption features more clearly. So here comes the measurements. In the left plot here, I showed the comparison between the gas phase oxygen with the stellar phase iron. So this is like the typical stellar Z gas Z plot you may have already seen in the previous paper. While on the right here, I showed, to my knowledge, probably the first ever comparison of alpha elements in the stars to the one in the ISM beyond the local group. And the black dashed line two panels are really the one-to-one line indicating the solar abundance pattern. So when we compare these two plots, we can see both from the ion, also from the statistics, the magnesium indeed tracks oxygen more closely. not only in terms of the absolute value, but also in terms of how tight the relation is. And so first of all, it definitely shows that magnesium is probably a better element to be compared with oxygen if we want to understand more physics behind it. Another thing I want to point it out is that you may notice most of the galaxies in our sample actually have higher oxygen abundance. So this is really interesting because the oxygen abundance in the ISM basically reflect the current chemical enrichment level, while the magnesium locked into the stars is the chemical enrichment level of the stars that form at an earlier epoch. And the excess in the gas phase oxygen here basically suggests that the current star formation is probably built on the well-mixed ISM that has already been enriched by previous generation of stars. So this is really contradictory to some theories saying that, at least for these galaxies, the star formation is powered by the external accretion from the surrounding environment. Because in that case, we actually should expect a lower oxygen abundance instead. Another thing we really care about is what is the shape of the stellar MZR, because that is really the the initial motivation for this project. And from all the analyses on the gas phase MZR, people have already figured out that in addition to the mass, the gas phase metallicity measured as the oxygen abundance has a really strong dependence on the star formation rate. As we can see in this plot, basically at a fixed stellar mass, galaxies with higher star formation rate tend to be more metal poor. And this is really because these highly star-forming galaxies have a lot of gas in it, and that really diluted metallicity within the ISM. So what would be the case for the stars? It turns out that it's actually a little bit complicated if you look at the stellar MZR in the local universe. So we know that in the local group, all the dwarf satellite galaxies fall on one universal stellar MZR, whether they are star-forming or quiescent. In other words, we do not see strong dependence on the star formation rate in terms of the stellar MZR for dwarf satellite galaxy. But if you look at more massive galaxies probed by those very large spectroscopy surveys, people have already found some evidence saying that the normalization is probably related to the star formation rate. But the uncertainties are pretty large, and also it is highly dependent on the model assumed in their work. So we want to figure out what would be the case for our sample as well. And that's why we also construct our own stellar MZRs, not only for the iron on the left, but also for the magnesium on the right. So here I show basically all the rectangles with gray color bars are our KCWI sample, the star-forming galaxies, while the two stars are the two quiescent galaxies in our sample. And also to make a fair comparison, we actually remeasured the stellar abundances for a sample of Sloan galaxies, quiescent and star-forming, using our new two-step method, just to minimize the systematic difference introduced into this comparison. So there are two main takeaways from the plot. First of all, if you compare the star-forming galaxies, which are all color-coded by their specific star formation rate, with the quiescent galaxies shown by these open circles, you can definitely notice that the scatter in the quiescent MZR is smaller. On the other hand, if we pay attention to the color bar, we definitely have seen some potential dependence on the specific star formation rate in terms of their stellar metallicity. So we can focus on the, especially our KCW sample here, at a similar stellar masses, galaxies with higher specific star formation rate, so more greener, tend to be more metal poor compared to the galaxies with lower specific star formation rate. So this basically means that as the galaxies become more and more quiescent, with decreasing specific star formation rate, they definitely become more chemically involved. So this again supports the starvation mechanism I mentioned earlier. So the galaxy just keep running out of gas, becomes more and more enriched, and finally it just stops forming stars. And in addition to all the things I've mentioned here are really on the global abundance, and we definitely need to think about something else. There are a lot of things that we have already seen in our galaxy. For instance, the data cube, one of the galaxy in our sample definitely show very significant spatial variation in terms of the spectral features. That really means the different parts of the galaxies host the stars from at different ages. And basically, by studying these spatial variations, we'll be able to reconstruct the evolutionary history within the galaxy. Another thing I really wanted to show is, this is really preliminary data, but I find it really cool, is that we maybe find an interesting galaxy. So this is a dwarf galaxy, a star-forming dwarf galaxies at around 10 to the 8.5 solar masses. So you can see that the spectrum for the core basically shows there's like very intense star formation activity going on. But there's a tidal tail. And if you check the spectrum, especially on the blue end, we can see a lot of only the Balmer absorption lines. So that means that this tail has been completely quenched and it is gas-free. And also based on the stellar kinematic study, the core and the tail only has velocity difference around 10 kilometers per second. So it is very likely that these two parts are linked together. So this can be something cool to look at. Overall, this is a really richful data set with a lot of interesting things going on. And I know I'm running out of time, so I'll just stop here and take questions. Thank you.